A continuación tenemos la ponencia Modelo de transportación binacional para la región Paso del Norte con el maestro en Ingeniería Jeff Shelton del Transportation Institute, Texas A&M.
El maestro en Ingeniería Civil Jeff Shelton recibió sus grados de ingeniero y maestro en Ingeniería de la Universidad de Texas en El Paso. Es investigador asociado en el Instituto del Transporte de la Universidad de Texas A&M y gerente de la oficina del Programa de Investigación e Implementación en El Paso. Su carrera profesional le ha permitido ganar experiencia en modelos de simulación y administración de carriles, carreteras, autopistas, tanto por sí solas como en conjunto, así como estudios y planeación de operaciones fronterizas. Es considerado experto en el concepto de modelación con multisoluciones por la Administración Federal de Carreteras, el Federal Highway Administration, y la Organización de Planeación Metropolitana, los MPOs, ambas asociadas al Departamento de Transporte de los Estados Unidos. Además, continúa estudiando el doctorado en Ingeniería Civil en la Universidad de Texas en El Paso. Por favor, adelante.
Hello, excuse me. Hello, everybody. Thank you for the formal introduction. When I go out with my wife, excuse me, she tells people I play video games for a living, so this is a little more formal introduction. I work for Texas A&M Transportation Institute, which is the largest transportation research institute in the nation. Even though I'm based in El Paso, we have office. The main office campus is on the main campus in Texas A&M University in College Station. But we have offices in Dallas, Arlington, Houston, Austin, El Paso, Mexico City, and Washington, D.C. So I'm going to kind of change gears a little bit to the presentations you've been seeing, and this is kind of more geared towards a transportation aspect as it pertains to binationally modeling how vehicles flow back and forth across the border. Well, El Paso is the second largest port of entry for crossing freight traffic in Texas. The only one that has more freight traffic crossing is Laredo. So this is in terms of billions of dollars of trade. So Texas has about $51 billion of trade going back and forth through the El Paso ports of entry. We have 3 ports of entry there. We have Zaragoza, the Bridge of the Americas, or we call it BOTA for short. Santa Fe, which is not a commercial port of entry. And then we have Santa Teresa crossing in New Mexico, but it's part of our Paso del Norte region. And so we kind of call that our sister port. So when you're trying to model a binational region, there's a lot of pieces that come into play. It's very complex. You know, you have to start considering arrival rates, the inspection times at the borders, what type of vehicles are crossing besides cars and trucks. We have pedestrians also. The time of the day and the day of the week really influences the amount of congestion you have at the borders. I did mention we have multiple border crossings. And then once you get to the ports, you have primary and secondary inspections. So what we're trying to do is build models to simulate all kinds of what-if scenarios. What would happen if this extreme event happened, if there's too much congestion, if you want to build a new port of entry. But since you have all these moving parts, it becomes very complex when you're talking about a binational region. So there's no one model or modeling platform that can answer all questions. Thank you. Excuse me. There's 3 types of modeling platforms. There's macroscopic or planning models. The MPOs usually use those. Those are mesoscopic. Those are still regional models, but they're simulation based, so they have a time component in there. And then microscopic, which is kind of the smaller scale individual cars and pedestrians. So what we're trying to do is we're trying to integrate these modeling platforms together to provide a more cohesive and optimal modeling platform. So what is multi-resolution modeling? So we're taking the strengths of all these model platforms. The macro models are kind of the foundation. Those give you the blueprint of the network, which is the streets. It also provides the origin destinations or where people are coming from and where they're going. Mesoscopic is region-wide, but it's simulation-based, so it has a time component on there. The macro models are mostly planning models. They have no time component. They just run equations, and they'll just tell you at the end of the day, this many vehicles traveled on the freeway. They'll just give you one number. You can't look at queuing. It doesn't have signals. It doesn't have a time component. Also, planning models can give you a volume to capacity ratio greater than 1. In reality, you can't have that. It doesn't exist. You can't stack cars on the freeway. Okay, so what we're doing is we're converting our planning model into a meso model, which has all this time component simulation. It has traffic signals. You can model delays, accidents, work zones, all kinds of stuff in the meso model. But it's still a regional model. It's still link-based, so you don't really see individual cars. Okay, it's still kind of like you're 1,000 feet in the air. The micro model is more individual cars and lanes. So why is it important? Models are not mutually exclusive. There is no one model platform that can answer all your questions. They're complementary to one another. And so when you integrate them all, you can accomplish optimal modeling capabilities. So what we're trying to do is we're trying to retain the best characteristics of each model. So from the planning model, you can incorporate multiple trip purposes. From the mesoscopic model, realistic representation of regional traffic and diversion when there's congestion. And at the micro level, detailed interactions. So what did we do once we have all these models, these modeling platforms? Well, we developed a binational model in TransCAD. TransCAD is a planning model. This is an image of El Paso and Juarez together. We have the El Paso MPO model. We took that, we went to EMIP, who's the planning organization in Juarez, and we got their planning model and we integrated them together. This includes all the ports of entry, even in Santa Teresa. We have traffic analysis zones, or the OD pairs as we call it, compatible with El Paso MPO. So we had to map trips going back and forth across the border, and that was very difficult to do. And we also have separate matrices or trips for cars and trucks. So once we had that planning model built in TransCAD or macroscopic, we converted it to mesoscopic. That acronym up there, DTA, means dynamic traffic assignment. The planning model is a static assignment. I mentioned there's no time component. Dynamic has a time component, so you see congestion building and dissipating. We built it for 24 hours, so we had 24 one-hour matrices, so we could look at traffic for the entire day. And we built matrices for both cars and trucks. And we also developed microscopic models of Boda and Saragossa. These are higher details, so you can look at individual lanes, lane assignments, queuing. What is the impact if you have more inspection delays when CBP starts inspecting vehicles and they're doing more thorough inspections? How does that impact the queuing and the delay at the bridge? You can model multiple modes of transport, cars, trucks, transits, pedestrians, bikes, even rail in the micro level. It gives you realistic driver behavior, and you can even have 2 and 3D graphics. 3D graphics are great for non-technical people. So what tool to use? So for regional analysis, I mentioned we developed a mesoscopic model for the region. We're able to paint a broader picture for traffic patterns binationally, simulate the impacts at multiple points of entry at the same time, and diversions due to congestion. At the individual point of entries, we use a micromodel because it just provides local output at the localized level. And so when we work close with CBP, it helps them make staffing decisions too, as far as how many inspection officers there should be for certain times of the day. When they close booths, what is the impact? How far does it start queuing back? What is the travel time? So the first project that we did was a freight regulatory plan in Juarez. So what we wanted to do is develop a binational model of El Paso and Juarez in the simulation-based. The freight regulatory plan was to look at how freight was moving in Juarez and how it was crossing the border. There is current plans in place. This was a large project that included the legality portion of it that another attorney helped us with as far as that. But from the modeling perspective, we started looking at different scenarios. So we're looking at updating the existing regulations, defining official freight routes. There's a lot of trucks that drive on routes that aren't designated as freight routes. Define clearly the scope and attributions of authorities on who's doing what. So what we did is we started looking at all these scenarios. We looked at the existing infrastructure. We started looking at the routes they were taking, and we started analyzing what could be done to improve freight traffic. So we started closing roads. We started talking to multiple freight carriers in Juarez. Sotelo is one of the biggest ones. We had several meetings with them to talk to them and see how the existing infrastructure worked for their freight, what is the best practices, what times do they leave. The bridges aren't open 24 hours a day for freight. They close at midnight, they open at 6. So that's a big problem for trucks crossing, especially when they're coming up from interior of Mexico trying to cross. They have to wait at the ports of entry until the bridge is open at 6 in the morning. So we were identifying all these problems and trying to come up with strategies on helping improve the freight flow in and around Juarez. So the first thing we had to do is we had to understand the movement. So we focused around the maquiladoras because that's the majority of where the freight traffic is in there. We had a PhD student that was working with us that also was teaching in Juarez. So we had some of his students come and help us collect a bunch of data as far as traffic counts. We were able to get traffic signals, all this kind of data that's needed to run a simulation-based model to calibrate it. So then once we started understanding the origins and destinations of these trucks, then we were able to run scenarios, determine the optimal truck routes for Mexican trucks, for Mexican truckers. Closing some of the roads that they didn't want freight driving on. There was smaller streets that had a lot of freight traffic, and the officials there wanted to close those. So what would that impact be? You have new routes. We also shifted some of the freight traffic to rail trips because they have a rail yard there. And I think they call them embarques in Mexico. Right. So we're looking at that, and we were looking at the impact of flow. So over there in the red, the thicker the line is, that's the heavier the flow is. So this is the port of it. This is the bridge, actually. That's the boundary of El Paso and Juarez. And that's Interstate 10 in the United States in El Paso. So all this is kind of where the maquiladora industry is. So when we started closing routes and putting in new routes, we started to see how the traffic would shift. Nobody had really done this from a simulation-based point of view. They would always do it with a planning model, but you can't really look at it at any given time of the day. The second project we did was an extreme events project. Our MPO director came to us and he said that there was really no resiliency plan for El Paso if we had a major incident where the Boda bridge closed for an extended period of time. So he asked us, okay, what I want you guys to do is model a scenario where the Boda bridge is completely closed, shut down. Just picture a hypothetical situation that there was an earthquake and it collapsed the whole bridge. And we also collapsed the interchange just north of that in El Paso. So what we did is we started looking at all the data, all the simulation of all this stuff, all the freight movements, all the commodities crossing back and forth from El Paso to Juarez, specifically at the Boda area. And we have 3 ports of entry. Boda's right about here. And then we have the Santa Teresa's way over here, and Zaragoza's down here. But we're collapsing the Boda bridge. So the questions, they said, okay, well, do a bunch of what-if scenarios. What is the impacts of the bridges at the other bridges if you close Boda? Capture the diversion. What is the short-term and long-term impacts? And from there, they wanted us to come up with an economic impact of the closure. So here's the 3 bridges I had mentioned. So the Boda bridge is closed for an extended period of time. And then the vehicles are rerouting to alternate bridges, okay? I have a short video here for you. So here's the commodity flows coming up from Mexico into the United States. Here's the two scenarios. So we're collapsing the Boda Bridge here, as well as the interchange in I-10, US 54 in El Paso. So here's the model running. You can start seeing traffic building throughout the day. Here's the bridge. So now we simulated the closure of this bridge or critical infrastructure failure. This is short term. This is immediately after it happens. So congestion on Interstate 10 is just basically at a standstill. This is in Juarez. You can see the traffic building. Okay, after an extended period of time, maybe a month or so, when people are just used to the bridge being closed and they start to reroute, now you can start seeing the streets in Juarez are getting more congested and the trips are shifting to the other bridges. What we started to see is the Zaragoza and Santa Teresa bridges can't accommodate the additional traffic. So what does this mean? So before the event, this was travel time for trucks. This is all of them through the entire simulation period, so this is averaged. And then after the long term, you can see that after equilibrium set in and people started finding alternate ways to get across the border, the travel time went down. And here's kind of the economic impact throughout the day for the shippers and carriers. This is first order direct costs. So we're not even taking into account fuel for alternate routing. This is short term and long term. So in the short term, when they really can't get across in this kind of chaos at the border, you can see what the cost is. Okay, and then we're getting down to the detailed analysis. So we did a couple studies of detailed analysis at the bridges. First was to determine the commuting costs of passengers at Boda. So we developed a microscopic model of the bridge, and we simulated a number of various inspection stations, inspection times, and we did another emissions study for Zaragoza Port of Entry. So at Boda, we wanted to quantify the monetary impact of northbound traffic. This is based on the number of booths open. So we're deriving the value of travel time savings to calculate the commuting cost. So you can see as the number of booths open increases, the amount of fuel consumption decreases. So you can see the correlation there. The more bridges or the more inspection booths that are open, the less fuel is being consumed by vehicles just sitting at the bridge waiting to cross. So here's a dollar amount for the total commuting cost, including insurance, fuel, maintenance, CO2 costs. We factored that in. So if you have 11 lanes open at Boda, approximately $21 million. And as you increase more lanes, you can see it dropping significantly. The last study we did was an environmental or emission study at Zaragoza. So we wanted to determine what the impact would be from passenger cars and trucks crossing northbound. So we developed a microscopic model of the Zaragoza Port of Entry. So we were testing scenarios of number of inspection booths open and the inspection time per vehicle. This is the number of inspection booths open in the northbound direction. Blue is commercial lanes, and I mentioned that they're closed from midnight to 6 o'clock in the morning, so you don't see any blue here. And then you have sentry lanes and standard lanes. So this is the average waiting time for passenger vehicles throughout the day. We have standard lanes, sentry lanes, northbound, and then these are the southbound. Commercial trucks, the average waiting time for them crossing this bridge, we found out that they would be parking right at the bridge at 6 o'clock in the morning to cross. So there's substantial queuing, but once they're able to get to the inspection booths, it was relatively quick, about 20 minutes of inspection time. And now throughout the day, once you get to the afternoon peak period, is when it really went over an hour of wait time for these trucks across the bridge. So from that, we ran that simulation model output into MOVES, which is an emissions model developed by Federal Highway. And we could calculate emissions for all kinds of different pollutants, so carbon monoxide, dioxide, NOx, PM10, PM2.5. We did this for cars and trucks separately. And then what we did is we reduced the number of capacity in addition to the reduction of wait times to see what would be the impact of emissions. So when we started doing all this modeling, trying to present all these results to our elected officials, decision makers, and they really don't have a technical background. So a lot of times we'd have to build tools like this to show them visually instead of numbers and graphs and charts, because they didn't really understand that. So this is a 3D model of the Boda port of entry. It's not congested fully because the model's barely starting to load with vehicles. Over here is primary inspection, and then the trucks come off over here into secondary after that. And then this is the passenger vehicles with the pedestrians crossing in the middle right here. So this is just a quick presentation of what we've done. We've developed a binational model in simulation-based format. I don't think anybody's really done that at this scale. These models do take time to build, so it is tedious and time-consuming. It does cost money to do it, but once you build them and you have them properly calibrated, you can run all kinds of scenarios. So, you know, what is the impact of tolls? You know, in El Paso, sometimes, or in Juarez, we have protests that just close down the bridge for a couple hours, where protesters all just sit there and block the bridge. So what is the impact for those 3 or 4 hours? So having these tools in place, you can answer a lot of questions. And that's it for my presentation.